So in the last section, we did derivatives, and each time we did it, we got a number as an answer. Now we are going to find derivatives, but instead of getting a number as an answer, we'll get a function as an answer. So again, we can use the limit as x approaches a, and then it's the difference quotient, f of x minus f of a over x minus a. Or you can get the same answer by doing the limit as h approaches 0, and then it's going to be f of x plus h minus f of x over h. And no matter which way you do it, you'll end up with the same answer. Now there's one small detail. When you finish this one, it will give you an answer like x squared. And you're done. When you finish this one, because it's x approaches a, it's going to say a squared. So then there would be just one last step. Replace the a in a squared with x, so it's x squared. So for example number 1, find the derivative of the function x cubed minus 2. And then which one should we use? This one or this one? Sounds like I got more votes for this one, so we're going to use this one. So it's going to be the limit as x approaches a, and then whatever the function is, you just put it right here. So this is going to be the x cubed minus 2. And then minus, substitute the function when it's got an a in it. So minus, it's important to put that parenthesis because this minus applies to everything that follows. Now it's going to be a cubed minus 2. And then it gets divided by x minus a. When you distribute this negative, that 2 right there is going to become positive, and that negative 2, they're going to cancel. So that means that after I write down the limit as x approaches a, that means that the numerator has x cubed minus a cubed. And then if x would become was to become an a, this would cause division by 0. So that means that we need to do algebra. And the algebra that we need to do is factor this using the difference of cubes formula. So that's going to look like x minus a, and then x gets squared. So when this is a minus, this starts off minus, and then it switches to be plus. You multiply the a and the x, and then a gets squared. And just like always, this thing cancels, so that right there is where we're canceling out the division by 0. And then all of these x's, according to this, all of these x's can become a's. So then it would be a squared plus a times a plus another a squared, which means that it's a squared plus another a squared plus another a squared. So that means there's 3a squared. Now because x has become an a, that means a has also become an x. So you could replace it and say, or it's 3x squared. And since the original function had an x, it's better to have the answer with an x. Now pretty soon we're going to have a shortcut to do this. I realize you'd be disappointed that we don't get to do this for the rest of the semester, but pretty soon you'll just look at that and say the answer is 3x squared. The fast way to do it is called the power rule. You take this power, you bring it down in front and multiply, that's that 3. Then subtract 1 from the exponent, that's a 2. And because the derivative is telling you the slope, this, if you were to graph just this part, y equals the negative 2, that is a horizontal line, and the slope of a horizontal line is 0. So the derivative of negative 2 is 0. That means this one is complete. Then how about example number 2? Find the derivative of 1 over x. So, by the way, a little bit of notation. To have to say this every time and to remember how to spell derivative each and every time, that's a lot of work. So there's actually notation for that. And that is, let's say that f of x is the original function. Then if you put a prime right here, that means derivative. Okay, so then let's find f prime for this one. So as I mentioned before, we've got these two definitions. Last time I used this one, so now we'll use this one. So f prime of x equals the limit as h approaches 0. It's f of x plus h minus f of x over h. That's the general definition. In this case, it's going to be the limit as h approaches 0, 1 over x plus h minus 1 over x, and then it's still divided by h. What we should do to simplify this one is get the least common denominator. So you look at the denominator x and the x plus h. The common denominator would be x times x plus h. And then multiply on the top by that common denominator and multiply on the bottom. Then on the bottom, you do not multiply it out, you just copy it down exactly as it is, h times x plus h. On the top right here, the x plus h's are going to cancel, it just leaves x. And on this one, the x's are going to cancel, but I need to distribute the negative. So it's going to be negative x and also minus h. So then the red pen says that these are going to cancel, so what it leaves is a negative h on top, and then h and x plus h on the bottom. Next, have these h's cancel, so it leaves just negative 1 on the top. And then h can become a 0, which means this is x plus 0, or just x. And then times that x means that the denominator has x squared. So that is the derivative. Notice that this one is undefined. When x equals 0, because it would cause division by 0. And in fact, the function itself is undefined when x equals 0, so it makes sense it does not have a derivative if the function itself doesn't even exist. Now back to that notation. So you can use the prime notation, f prime of x, or sometimes the function is just y equals something, so the derivative would be y prime. You can also say the derivative of some function with respect to x. So this is saying the derivative, and then this is saying that the variable is x. You could also say dy dx, which, if you remember where the definition of the derivative comes from, it comes from slope. And slope is y2 minus y1 over x2 minus x1. Or in other words, it's the difference of the y's over the difference of the x's. That's sort of what this is talking about right here. But they're all ways to say derivative. Now with this one, it might be that you would then write the function in there. What's the derivative of happy face? Of course, it's not going to be happy face, but maybe sine of x or 1 over x squared or something like that. Then on to the next idea. Does the derivative always exist? And of course the answer is no. For example, right there, we saw that the derivative exists except when x equals 0, because that would be undefined. So the original function needs to be continuous if it's going to have a derivative. This is not continuous when x equals 0, so the derivative does not exist when x equals 0. So for one thing, the function must be continuous. But there are even examples of functions that are continuous and yet the derivative does not exist. There's basically 3 possibilities for that. One is if you have a function that goes like this and it makes a sharp corner. So right here, which is actually called a corner, the derivative does not exist right there. The reason is the definition of the derivative is that it's a limit, and the left side and the right side have to agree. Well, with this one, this has a slope of approximately positive 1. And on this side, the slope is approximately negative 1. So at that point right there, is the slope positive 1 or is the slope negative 1? It cannot have 2 answers. Then there's a shape that's similar to that, except it's much, much sharper. It goes like this. So basically the function is pretty much going vertical and then it goes back down. This is called a cusp. And the derivative does not exist at that point. And there's one other possibility, and that is the function's going along fine, and then for a moment it basically goes vertical. And for a vertical line, because the tangent line for this one would be vertical, that is undefined slope. So right in here, you would have a vertical tangent line. So these 3 are examples where the functions are continuous, but the derivative does not exist. So let me call this point A, f prime of A does not exist. All right. Now for example number 3. How about if y is equal to the absolute value of x? So what is the absolute value of x equal? Well, let me finish my question. I forgot to do that. Where is y prime undefined? Where is it that the derivative does not exist? So let's see. First of all, to graph it. So go to y equals, and then to get the absolute value, go over here to math, and then move over to number. And ABS, you may think is anti-lock braking system, but it stands for absolute value. And depending on your operating system, it'll either put the straight lines like I put that, or it'll put ABS. So the absolute value of x, and then I'm going to go to zoom standard, and it's a V shape. So over here, the derivative would exist, and this is a slope of -1, so the derivative would equal -1. Over here, this is a slope of +1, and right there at 0, the derivative does not exist. So that is an example of a corner, the absolute value function. So y prime of 0 does not exist. For example number 4, how about if y is equal to x is to the 2/3 power? Again, where is y prime undefined? So if you graph that one, it's going to be, let me clear out the old one, x is raised to the 2 divided by 3, 2/3 power. And then zoom standard. At first, it looks like it's similar. So right there, it bounced off the x-axis. All of this is fine, 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 but what's happening at the origin? So let me zoom in. And then hopefully you can see that that is a cusp. Let me just zoom in one more time. And so when it bounces, it makes that sharp point right there. That's a cusp. So the derivative does not exist when x equals 0. So this one comes in, it bounces off the x-axis, and then that is a cusp. I forgot to say or write down, that one is a corner. So y prime at 0 ne existe pas. And then for example number 5, how about y equals, what if we do the cube root of x? So is there any place where the derivative doesn't exist for that one? So y equals, and then I could write it as x raised to the 1/3. That'll be the cube root. Or I could go to math, and then the fourth one down is the cube root, and do the cube root of x, zoom standard, and then right there at the origin, it went vertical just for a moment. So all of this part is fine, all of this part is fine, but right there it went vertical. So let me zoom in from -1 to 1, -1 to 1, and then take a look at the graph, and you'll see right here, you'll see the graphing calculator even got a little bit confused, and it didn't know how to connect that because it went vertical so fast. Actually, what's happening with the calculator is the way the calculator graphs is it actually puts dots in its brain, and then it connects the dots. And there was such a big gap right there, it didn't know what to write. Let me erase that now. So the derivative is not going to exist there. Now let me show you something even better. If you go right here to calculate, so it's in blue, so you'll need to go second calculate. Looking at those, can you guess which one is the derivative? That's right, it's dy dx. So tell it number 6, or go to 6 and hit enter. And right now, I'll just pick a point like over here. So like, how about at point 2? And it says, at that point, the derivative is equal to 0.975. All right, perfectly fine, it works. Then if you go to second calculate, and again, do the derivative, and you try 0. Now what it should say is undefined. Yeah, I know, I'm excited too. What it's supposed to say is undefined. Let's see if it actually does it. No, it said that the derivative is 100. So basically that point is confusing the calculator not only on graphing it, because you could see there's a hole in it, but also on the derivative. When I try any other point, take the derivative at a 0.5. Yep, it does it just fine. But at that point, 0, it actually makes a mistake. Sorry, I probably you thought I paid $100 for this calculator and it's never going to make mistakes, but technology does make mistakes. Now the math won't lie to you, but the calculator sometimes does. So this one, as it went through the origin, just for a moment it went vertical. So the derivative does not exist there. Then, for those of you that stuck around for the end of today's show, I want to show you another way to prove that I'm right and the calculator is wrong when it said the derivative equals 100. So that is, here's the faster way to find derivatives. So this, I could rewrite it as x to the 1/3. That's another way to write cube root. Then I'll find the derivative the fast way using the power rule. The power rule goes like this. Take the 1/3, bring it in front and multiply. And then subtract 1 from this exponent. And 1/3 minus 1 will be negative 2/3. So in other words, y prime is equal to 1. And I don't like to leave negative exponents, so I'm going to invert this. The 3 is on the bottom, and then x to the 2/3. So that is the derivative. And then if you take a 0 and plug it in for x, that is going to cause division by 0. So at 0, the derivative does not exist.